The other day, we talked about the basics of the nervous system and the structures of neurons, or the cells that make up our nervous system. And what we're going to talk about today is how those neurons actually work. How do they send a message from one neuron to the next in order to get our body to function? So, the first thing you have to realize is that inside and outside the neurons, there's always a constant movement of sodium and potassium ions. So, the extracellular fluids, or the fluid that surrounds our neurons, is going to have more sodium ions. And our intracellular fluids, or what's inside the neuron, like the cytoplasm, is going to have more potassium ions. And any change in movement of those potassium ions from the outside to the inside, or the potassium from the inside to the outside, is going to cause an electrical gradient within our neurons. And that electrical gradient can be measured by a voltmeter and graphed, which we'll look at those graphs later. So when a neuron's at rest, we call it resting potential. And when your neuron is at rest, we measure the electrical gradient at negative 70 millivolts. Remember that number. When neurons are at rest, they're at negative 70 millivolts. So this picture is showing you have your neuron. And when we're talking about resting potential, we're looking at the cell body because that's where the cytoplasm is going to be, and you're going to have the greatest potential, or the greatest, concentration of sodium and potassium there. So you can see at resting potential, if the neuron receives a stimulus, the graded potential is going to build up at the region where the cell body meets the axon. It's kind of that triangle part. It's called an axon hillock. And then if there's enough graded potential, it'll produce action potential, which is going to send that message down the axon, through the axon terminals, and hopefully to the next neuron. So this is just showing you what resting potential looks like. Remember, resting potential is at negative 70 millivolts. On the outside of the cell, there's going to be a greater concentration of sodium, which you can see in the purple. And on the inside, there's a greater concentration of potassium ions. So how neurons work is enable to get that concentration change between the inside and the outside of the cell. There has to be channels that allow those ions to pass through because they're too large to fit through the cell membrane. And there's two types of channels. There's passive leak channels that are always open, and that's creating that negative 70 millivolt potential. And then in order to have a change in membrane potential, the sodium and potassium have to go in and out of the cell using gated ion channels, or sometimes they're called ligand gated channels. So here's a picture of a leak channel, always open, the ions can flow through. But with a gated channel, something has to activate it in order for it to open up and allow those ions to go in, and then eventually it'll close. So how neuron works is if we change the movement of sodium and potassium, the change is called a local or graded potential. So those gated channels have opened up and there's been some movement of ions. If the voltage becomes more positive than negative 70 millivolts, we'll say that depolarization has occurred. If the voltage goes back to negative 70 millivolts, we'll say that repolarization has occurred. And if the voltage becomes more negative, we'll say that hyperpolarization has occurred. And we'll talk about these terms a little bit more when we look at a graph measuring a neuron's electrical potential. So these pictures are just showing you resting state and when the neuron is kind of receiving the stimulus and building that graded potential. And again, you can see the difference between like depolarization and repolarization and hyperpolarization here. Depolarization is when we're rising above negative 70 millivolts. Repolarization is when you go back to it, and hyperpolarization is when you dip below it. So when we look at the electricity in a neuron, we use something called a myogram. When you're reading a myogram, some important things to keep in mind is you need to know a stimulus. In order for the electrical gradient to change, there has to be a stimulus applied to our neuron. You need to remember that resting potential is negative 70 millivolts. That threshold is when we go above normal, so above that negative 70. And that threshold has to be exceeded for the all or none effect to happen. And what the all or none effect is when a neuron fires, it either fires completely or it doesn't fire at all. There's no halfway. And again, depolarization, when the cell becomes more positive. The absolute refractory period, which we'll look at a little bit later, has a specific part of the graph. Repolarization is when we go back to negative 70. Again, we'll look at relative refractory in a minute. And then hyperpolarization is going below negative 70 to kind of reset the neuron. So on this graph, it's showing you where your resting potential is, what that threshold potential is, and if that threshold potential gets passed, our neuron is going to fire. It's going to go through the depolarization stage, the repolarization stage, and then the hyperpolarization stage so it can set back to normal. So you can see here you have your absolute refractory period when you have that big peak between depolarization, repolarization, and your relative refractory period is when you're dipping below into that hyperpolarization stage. So now let's talk about, we have enough potential to pass our threshold and the action potential is going to get sent down the neuron. So this is kind of a long version. I broke it out for you in the next couple of slides. But the first thing that's going to happen, like I said before, is a stimulus causes a local electrical change at a dendrite. Remember, the dendrites are going to receive the message and they're going to send that message into the cell body. If the electrical charge is above normal or above the threshold, it's going to concentrate in the axon hillock, the region where the cell body meets the axon. And then the electrical charge is going to travel down the axon. And we call that electrical charge traveling down the axon action potential. The electrical charge is going to come to the end of the axon or at the synapse. When it reaches the synapse, there's going to be calcium ion channels that are going to open and they're going to bring calcium into the synapse. And this causes the release of neurotransmitters, and neurotransmitters are just chemical messengers that are stored in our vesicles at the end of our axon within the synapse. Those neurotransmitters are going to leave the synapse and enter the small space, which we call a synaptic cleft. It's a small space between the original neuron and the next neuron. And then excess neurotransmitters in the space get deactivated, but most neurotransmitters will go to the next neuron and they will start that sequence of action potential again. So I like to think of action potential in steps. It makes it a little more easy for me. So step 1 of action potential is depolarization, brings the cell membrane to the threshold potential of negative 60 millivolts. When that happens, step 2, the voltage-gated sodium channels open and sodium is going to flood into the cell and the cell becomes more positive, like we said, depolarization. Then step 3, those sodium channels close and potassium channels open up, and potassium is going to diffuse out of the cell, which causes the cell to become more negative or repolarization. And then finally you have step 4. Step 4, the membrane returns to its normal voltage, but first it has to go into hyperpolarization, which means it's going to dip down below that negative 70, and that's because all of our ion channels don't close at the same time, so there's going to be some inconsistent membrane potential across the axon. Like we said before, the period of time between the beginning of action potential and the return to the resting potential is called the refractory period, and no additional activity can occur at this time. The neuron cannot send another action potential until we get back to our resting potential. So really what action potential is all about is just ions going in and out of the cell, and that movement of ions creates an electrical charge that's able to send a message down the axon to release neurotransmitters that'll be received by our next neuron to cause a similar response. Again, we have our myogram showing us the different stages of action potential. So we talked about synapses a little bit before when I was explaining what action potential was. And synapses are located at the end of a neuron, and they're used to communicate with other cells via neurotransmitters, which are chemical messengers. So there's a couple types of synapses. There's electrical synapses, and electrical synapses require direct contact between cells. These are very, very rare. But what we talk a lot about in anatomy and in psychology is chemical synapses. Chemical synapses needs a presynaptic cell, which is like your original neuron, your synaptic cleft, the space between two neurons, and your postsynaptic cell, your second neuron that's going to be receiving the message. Synaptic delay and synaptic fatigue. Delay is when the neurotransmitters take a little bit longer to get across, and fatigue is when too many neurotransmitters are received. It becomes difficult for that receiving neuron to function. And then chemical synapses can be excitatory. They can inhibit things. They can accelerate things, or they can be inhibitory. They can stop them. And then these are very common, and these are just different types below listed, different types of neurotransmitters and how they're classified. And then the general function of neurons. If you've taken AP Psych, you talk about this in a lot more detail, but because of some vocab differences and some time, Constraints, we're not going to go a ton into this, but there's different ways that we can measure our postsynaptic potential. And that postsynaptic potential can be measured as excitatory. Does it increase action potential, and or inhibitory? Does it stop it? Temporal. Do many signals get sent over the same time? Or spatial. Does it get spread out through neurons? And that's where you're going to stop for today. So let me know if you have any questions next class, and good luck with your packet.